Hello everyone. In this lecture, I will discuss eigenvalues and eigenvectors. First of all, I will discuss characteristic equation. Let A is any square matrix of order n. Then the matrix A may be singular or non-singular, but we have to find characteristic equation first. Let I is identity matrix of order n, and lambda is any scalar. Then suppose we have a matrix A which is of order n. So we have n rows and n columns. Entries are a11, a12, and up to an. These are entries of first row. And similarly, we have entries of second row. And this is actually a matrix of order n. Now we have a matrix which is a minus lambda I, which is equals to this one, and which is also a matrix of order n by n, where I is entity matrix of order n. And this matrix is known as the characteristic matrix of matrix A. Now we have to find determinant of characteristic matrix A. So A minus lambda determinant will be this one, which is given by the determinant A11 minus lambda, A12, and so on. Then we have A1 n. Then we have A21, A22 minus lambda, and so on up to A2n. So lambda will be subtracted from diagonal elements of matrix A. Then we get this determinant, which is known as the characteristic determinant. And after solving this one, we get the characteristic polynomial of A. Now we come to the point which is the characteristic equation. The equation A minus lambda I determinant equals to 0 is known as the characteristic equation of matrix A. Now the main point which is eigenvalue. Eigenvalues are the roots of this characteristic equation, and these are, say, lambda 1, lambda 2 up to and so on. We have lambda n, and these are known as the characteristic roots or characteristic values. These are also known as the eigenvalues, latent values, or latent roots, or proper values of matrix A. Now we come to an example which is, we have to find the eigenvalues of matrix A, which is 5, 4, and 1, 2. Then let we have the matrix A equals to this one. Then characteristic equation will be A minus lambda I determinant equals to 0. That is 5 minus lambda, 4, 1, and 2 minus lambda equals to 0. Suppose we have to find A minus lambda I matrix. So A minus lambda I matrix, then determinant. So we have A. A is actually 5, 4, 1, and 2. Then we have minus lambda I. I is the identity matrix of same order. That is, we have 1, 0, 0, and 1. So we get 5 minus lambda, then 4, 1, and 2 minus lambda. So this is the characteristic matrix. If we have to find characteristic equation, then we have to write A minus lambda I determinant equals to 0. So we get this equation, which is 5 minus lambda, 4, 1, and 2 minus lambda determinant equals to 0, and which will be 5 minus lambda into 2 minus lambda and minus 4, which one equals to 0. And we get this equation, which is lambda square minus 7 lambda plus 6 equals to 0. We can directly find this equation with the help of some direct rule, which is for 2 by 2 matrix or matrix of order 2. The characteristic equation will be lambda square minus the trace of A, that is trace A actually sum of diagonal elements. So lambda square minus trace of A, then we have lambda and plus A determinant equals to 0. So here, since diagonal elements are 5 and 2, so we have sum as 7. So equation will be lambda square minus 7 lambda plus, here we have determinant which is 5 into 2 and minus 4, that is 10 minus 4, which is 6. So equation will be lambda square minus 7 lambda plus 6 equals to 0. So this is the characteristic equation for matrix A, and this is of 2 by 2 matrix. So we have equation of order of degree 2, and these are roots for this equation, and these are lambda equals to 1 and 6. These values are known as the eigenvalues of given matrix A. And similarly, we have one more matrix. This is a matrix order 3. And for this matrix, the characteristic equation will be obtained with the help of characteristic matrix. And so we have A minus lambda I, which is the matrix 2 minus 3 1 3 1 3 and minus 5 2 and minus 4, and minus lambda, and then identity matrix which is 1 0 0 0 1 0 and 0 0 1, and this is identity matrix of order 3. Now the characteristic matrix will be this one. So lambda will be subtracted from diagonal elements here. Now characteristic equation will be A minus lambda I determinant equals to 0, which is this one, and we can find this equation which is A minus lambda I determinant equals to 0, and after solving this determinant, we can solve this determinant which is this one. We can solve directly this determinant, and after solving this one, we get this equation which is a cubic in lambda. So this is the equation which is minus lambda cube minus lambda square plus lambda equals to 0. So we can solve this one with the help of expansion of determinant, and this is lambda cube plus lambda square minus 2 lambda equals to 0. And this is the required characteristic equation which we can find. And after solving this cubic, we get three characteristic values or eigenvalues here, or eigen roots or characteristic roots here, and these are 0, 1 and minus 2. So we can directly solve this one. This is cubic actually, and we can write here like this will be lambda and lambda square plus lambda minus 2 equals to 0. So we can make factors of this one. This is lambda square plus 2 lambda minus lambda and minus 2 here. So factors are here. This is lambda plus 2 and minus lambda plus 2 equals to 0. So we have lambda plus 2 common here, and we have lambda minus 1. So we have the roots as lambda equals to 0, minus 2 and 1. So these are the roots of this equation. So lambda equals to 0, 1 and minus 2, and these are characteristic values of this 3 by 3 matrix. Now this is alternative method to solve the characteristic equation. Here we have a matrix of order 3 by 3. For 2 by 2 I have discussed. For 2 by 2 matrix we have the characteristic equation which is lambda square minus trace of A, the lambda and plus A determinant equals to 0. This is the characteristic equation which we can write directly. And for 3 by 3 order matrix, we have characteristic equation as lambda cube and minus trace of A, lambda square plus A1 plus A2 plus AT. Actually, these are the minus corresponding to principal diagonal. The lambda minus A determinant equals to 0. Now we have to find trace. So what is the trace? Trace is actually the sum of diagonal elements. So first we have to find sum of diagonal elements. We have a matrix here which is 2, minus 3, 1, 3, 1 and 3, and minus 5, 2 and minus 4. So sum of diagonal element will be here 2 plus 1 and minus 4. So this is minus 1 here. So trace will be minus 1 here. Now we have to find A1, A2 and A3. So these are actually the minus corresponding to principal diagonal or corresponding to these entities here. So here we have to find the minus. So first minor will be this one, that is 2, minus 3, 3 and 1. And the second will be 1 from here, this one. So 1, 3, 2 and minus 4. And third one is actually 2, 1 and minus 5, minus 4. 2, 1, minus 5, 4 will be obtained with the help of this one, or leaving the second row and second column or corresponding to this entity we have. So we have 2, 1 and minus 5 and minus 4 here. So these are 3 minus here and minus A determinant. In this example, A determinant is actually 0. So the values of these minus actually we can find. The first minor will be we have 2 into 1, that is 2 minus 9. So we have 2 minus 9. So first one we have the 11. So first entity is actually 11. And second we have minus 4 minus 6, which is minus 10. And last one we have minus 4 plus 5, minus 8 plus 5. So we have minus 3 here. So this is the characteristic equation, which is lambda cube plus lambda square minus 2 lambda equals to 0. So again we have same values 0, 1 and minus 2, because we have the same example, but we have taken alternative method to solve this example or to make characteristic equation here. Now we have one more example here, in which we have to find the characteristic values of the matrix, which is 6, minus 2, 2, minus 2, 3 and minus 1, 2, minus 1 and 3. So first the characteristic equation of the given matrix A will be A minus lambda I determinant equals to 0. Now which is 6 minus lambda minus 2 and plus 2, then these are the entities here, and characteristic equation will be here lambda cube minus 12 lambda square plus 36 lambda minus 32. I will again discuss the method, same method I have discussed, lambda cube minus trace of A, trace of A. Then we have lambda square and plus we have the minus corresponding to principal diagonal. Then we have lambda and minus A determinant equals to 0. So here lambda cube minus trace will be the sum of diagonal elements. So we have 6 plus 3 plus 3. So we have 12 here. Then we can find the minus. So minus will be first one is 6 minus 2 and 3. So we have 1 minus. Next one we have 3 minus 1 and 3. And last one we have which is 6, 2 and 2, 3. 6, 2 and 2, 3. So values are 18 minus 4, that is first one is 14. Next we have 9 minus 1, that is 8. And last one we have 18 minus 4, that is 14. So sum is actually 36 here. So we can solve this one directly with the help of this method, which is lambda cube minus trace of A, lambda square and plus sum of minus corresponding to principal diagonal and minus determinant of A, which is 32 actually. Here in this example determinant is 32. So on solving this equation we get the values 2, 2 and 8, and these are characteristic values of eigenvalues. Now we have some properties related to eigenvalues or characteristic values. First one is if we have any square matrix A and suppose we have some eigenvalues, let us say we have 2 and 5 and these are eigenvalues of any matrix. Then if we have taken transpose of A, then eigenvalues will be same here. So if we have A matrix and eigenvalues are 2 and 5, then eigenvalues of A transpose are also 2 and 5. Now we have the second point, second important property. If lambda be an eigenvalue of a non-singular matrix A, then lambda inverse is also an eigenvalue of A inverse. It means suppose we have 2 and 5 and these are eigenvalues of any matrix of order 2, then eigenvalues of A inverse will be 2 inverse and 5, that is 1 upon 2 and 1 upon 5. These are the eigenvalues of A inverse. And also the eigenvalues of adjoint A is actually A determinant upon lambda. So for this example here, actually eigenvalues, suppose we have lambda 1, lambda 2 and we have to find determinant of A and we have a matrix of order 2. A very simple example here, that determinant equals to the product of eigenvalues here. I will discuss in last point here. So A determinant, suppose we have to find, then A determinant equals to the product of eigenvalues, product of eigenvalues. I will discuss in the last point here. So in this example, suppose eigenvalues are 2 and 5, then A determinant will be 2 into 5, that is 10. And suppose we have to find eigenvalues of adjoint A, then according to this one, eigenvalues of adjoint A is A determinant upon lambda. So corresponding to lambda equals to 2, eigenvalue will be 10 upon 2, because A determinant is 10 here. A determinant is 10 and lambda is 2 here. So first one is 10 upon 2 and second one is 10 upon 5, and this is corresponding to lambda equals to 5. So values are 5 and 2 here. So suppose we have 2 and 5 and these are eigenvalues corresponding to the matrix A, and we have a matrix of order 2, then eigenvalues of A inverse will be 1 upon 2 and 1 upon 5, and eigenvalues of adjoint A will be 5 and 2 according to this property here. Now, we have some more properties in which sum of eigenvalues of a matrix is equals to the trace of the matrix, or sum of eigenvalues equals to the sum of diagonal elements, because we know the trace of any matrix equals to the sum of diagonal elements. Now, the fourth point, the eigenvalues of A are lambda 1, lambda 2 and lambda 3, then the eigenvalues of A square will be lambda 1 square, lambda 2 square, lambda 3 square and so on. So, for this example here, suppose we have to find eigenvalues of this matrix, and suppose eigenvalues of A are 2 and 5, then eigenvalues of A square will be 2 square and 5 square. That is, eigenvalues of A square will be 4 and 25 here. So, these are eigenvalues of A square. And suppose we have the eigenvalues of any matrix lambda 1, lambda 2 and lambda 3, and then eigenvalues of A raised to m are lambda 1 raised to m, lambda 2 raised to m. For the example, suppose we have to find eigenvalues, then we get 2 raised to m and 5 raised to m. Suppose we have to find the eigenvalues of A raised to m, and if eigenvalues are 2 and 5, then we get 2 raised to m and 5 raised to m. And I have discussed already this property. The product of all eigenvalues of a matrix equals to the determinant of A. I have used this one in this second point actually. The product of eigenvalues of a matrix equals to the determinant of A. So, this is very important property, and we can find the eigenvalues of some matrix and relation with some expression given to us. Then we can find eigenvalues of these expressions very easily. Now, we have some example here. Let we have a matrix A, and then suppose we have to find the eigenvalues of this matrix, which is some expression given in the form of A. Now, first we have to find eigenvalues of A. If we have to find eigenvalues of A, then we have to make characteristic equation, then we have to solve this equation, we get eigenvalues. But there is one more very important property. If we have upper triangular matrix, or we have lower triangular matrix, or we have diagonal matrix. We have these three kind of matrices, then eigenvalues are diagonal elements. So, here in this example, we have an upper triangular matrix because the entries below the principal diagonal are 0. So, here in this example, eigenvalues will be the diagonal elements, and diagonal elements are 1, minus 2 and minus 3 here. But we can solve this equation or characteristic equation which is A minus lambda determinant equals to 0. So, we can make this equation, and which is lambda cube plus 4 lambda square plus lambda minus 6 equals to 0. So, on solving this equation, we get 1, minus 2 and minus 3. So, the eigenvalues are 1, minus 2 and minus 3 here. I have already discussed that for upper triangular matrix, the eigenvalues are the diagonal elements, and these elements are 1, minus 2 and minus 3 here. So, now we have to find eigenvalues of this expression which is given in the terms of matrix A. So, first we have to find eigenvalues of the first term, and for first term, first we have to find the eigenvalues of AQ, and eigenvalues of AQ will be according to the property as I have discussed. If eigenvalue of matrix A is lambda, then eigenvalue of A square will be lambda square, and eigenvalue of AQ will be lambda cube. So, here eigenvalue of AQ will be 1 cube, minus 2 cube and minus 3 cube. So, eigenvalues of AQ will be 1, minus 8 and minus 27 here. Similarly, eigenvalues of A square will be minus 1 square, minus 2 square, 1 square, minus 2 square and minus 3 square. So, we have 1, 4 and 9. These are eigenvalues of A square. Now, eigenvalues of A are given here. These are 1, minus 2 and minus 3. And as we know, eigenvalues of identity matrix are always 1. Suppose we have any matrix of order 2 by 2 and that is this one, and this is identity matrix. And I have discussed this property here. The eigenvalues of diagonal elements are the elements corresponding to principal diagonal or diagonal elements directly we can say. So, eigenvalues are 1 and 1. Suppose we have 3 by 3 order matrix. So, we have this one, and again the eigenvalues are 1, 1 and 1. So, these are eigenvalues. So, eigenvalues of identity matrix are 1, 1 and 1 here. Now, we have to find eigenvalues of this whole expression. So, what will be the eigenvalues of this expression? Now, first we have to find eigenvalues corresponding to first eigenvalue, which is 1 here. So, for first expression, we have to put 1 in this expression in place of A. We get eigenvalue of this expression corresponding to the first eigenvalue, which is lambda equals to 1. So, we get 3 into 1 cube, then we have 5 into 1 square, then 6 into 1, and then we have 1, which is eigenvalue of I, and the sum will be 15. So, 15 is the eigenvalue of this expression corresponding to lambda equals to 1, which is eigenvalue of the given matrix A. Now, come to the second eigenvalue. Second eigenvalue will be corresponding to lambda equals to minus 2. So, we have to put lambda equals to minus 2 in place of A here. So, we get 3, then we have minus 2 cube, which is minus 8, then we have 5 into minus 2 square, which is 4, and 6 into minus 2, then plus we have I means eigenvalue of identity matrix, which is 1 here. Now, after solving this whole expression, we get minus 15. So, minus 15 is the eigenvalue corresponding to lambda equals to minus 2. Now, come to the third eigenvalue. So, we have to put here minus 3 in place of A, because we are finding here the third eigenvalue corresponding to eigenvalue lambda equals to minus 3. So, we have to put here minus 2 cube, which is minus 27, minus 3 cube will be minus 27, minus 3 square will be 9, and we have minus 3. Then last sum we have the 1, which is eigenvalue corresponding to identity matrix, which is 1 here. So, after solving this, we get minus 53. So, 15, minus 15 and minus 15, 53. These are the eigenvalues of given expression corresponding to the eigenvalues 1, minus 2 and minus 3, and these are eigenvalues of matrix A. Now, come to the very important part of this one, and the second topic of this class, which is eigen vector. So, what is eigen vector? This is a non-zero column vector and corresponding to any eigenvalue, which is known as the eigen vector. Then how to find this eigen vector, or what is the eigen vector actually? Eigen vector is the solution of this equation. Suppose we have 2 by 2 order matrix, then we have a column matrix of order 2. It means we have entity of this kind, yani x1 and x2. So, we have this one as eigen vector. If we have a matrix A, which is square matrix of order 2, then this will be the eigen vector corresponding to a particular eigenvalue lambda. If we have A matrix, which is matrix of order 3, then we get a vector which is x1, x2 and x3. So, this is the eigen vector. Suppose we have a matrix A which is of order n, then we get the eigen vector which is x, and this is eigen vector corresponding to eigenvalue lambda, and which is the solution of this equation, and this is known as the eigen vector, or we also told this one as characteristic vector. Now, we have some example here. First, we have an example of order 2. Find the eigenvalues and corresponding eigenvectors of the matrix. We have a matrix of order 2 by 2, and we can find first one, we have to find eigenvalues. For this one, first we have to find characteristic equation, and we have a matrix of order 2 by 2. So, we can directly find the characteristic equation, which will be lambda square minus sum of diagonal elements, and this is actually minus 7. Then we have determinant of lambda, then we have determinant of it, which is minus 5 into minus 2, which is 10, and minus 4, it means we have 6. So this is the characteristic equation here, or we can solve this one by solving this determinant. We get the characteristic equation, which is lambda square plus 7 lambda plus 6 equals to 0. Now we can solve this equation, and after solution we get the values lambda equals to minus 1 and minus 6 here. Now we have to find the eigenvector corresponding to eigenvalue lambda equals to minus 1, because we have different eigenvectors according to different eigenvalues. Here we have two eigenvalues, lambda equals to minus 1 and lambda equals to minus 6. First we have to find eigenvalue corresponding to lambda equals to minus 1. So as we know, if we have a matrix of order 2, then eigenvector will be in this form here. Let x1, x2 will be the eigenvector corresponding to eigenvalue lambda equals to minus 1 here. So eigenvalue we have lambda equals to minus 1, then the corresponding eigenvector will be the solution of this equation. Here we have lambda is minus 1, so we get solution of this equation, which is a plus I x1 equals to 0. Here we have to find the matrix x1 or vector x1 here. Now after putting the values of a and lambda, we get this system of equations, and after writing in this equation form, we get minus 4x1 plus 2x2 equals to 0, or we have 2x1 equals to x2. This is actually homogeneous system of equations. Let x1 is k, then x2 will be 2k here. Then the vector will be k and 2k here. So this is the required eigenvector corresponding to eigenvalue lambda equals to minus 1 here. So we can solve this equation. As we know, we have the similar equations here, and we have one equation. So first we have to assume any of the variables x1 or x2 as some arbitrary number, and here we have assumed that x1 is k, x1 is any arbitrary number, and x2 will be 2k. So we have a vector which is k and 2k, where k is any arbitrary number. Now we have to find eigenvector corresponding to eigenvalue lambda equals to minus 6, and let this vector is actually x2, which is x1 and x2. Then again we have the system here, which is a minus lambda I x2 equals to 0, and lambda is minus 6 here. So we have a plus 6I x1 equals to 0. Now we have to find solution of this system of equations, which is 1, 2 and 2, 4, x1, x2, then we have 0, 0 here. So we get this equation, and again we have to assume any of the variables as some arbitrary number. Let x2 is k, then x1 will be minus 2k. So we get the vector x2, which is minus 2k and k. So we get k, minus 2 and 1, which is the eigenvector corresponding to eigenvalue lambda equals to minus 6. So this is an example of a matrix of order 2 here. Now come to the other example, which is example of a matrix of order 3. Let we have an example, and in this example we are seeing here, this is example of upper triangular matrix here. So as we know, eigenvalues of upper triangular matrix are the entries of principal diagonal actually, or elements of principal diagonal. So eigenvalues will be 3, 2 and 5 here, but we have to solve in a process here. First we have to find characteristic equation, which is a minus lambda I determinant equals to 0, and after solving this one we get the values 2, 3 and 5. Here we have a matrix of order 3, so we have 3 eigenvalues. Now we have to find the eigenvectors corresponding to these values. So first we have to find eigenvector corresponding to lambda equals to 2, and let this vector is x1, x2 and x3. Then actually this vector will be the solution of this equation. So after putting the values of lambda and a, we get this system of equations here, and from this system we are seeing the first equation will be x1 plus x2 plus 4 x3 equals to 0, and we have 6 x3 equal to 0, and we have 3 x3 equal to 0. So from this one we are seeing that x3 is 0 actually. And after putting this equation, we get x1 plus x2 equals to 0. So here we have x3 as 0 and x1 plus x2 will be 0. So first we have to assume any of the x1 or x2 as some arbitrary number. So here we can solve also by the help of cross multiplication. But if we solve this system, as we know that x1 plus x2 equals to 0. If we assume x1 as k, then x2 will be minus k. And we have x3 as 0. So x1 is k, x2 is minus k, and x3 is 0. So we get k minus k and 0 as the eigenvector corresponding to lambda equals to 3, or k 1 minus 1 and 0 corresponding to eigenvalue lambda equals to 2, where k is any arbitrary number. Now we have to find eigenvector corresponding to eigenvalue lambda equals to 3, and let this vector is x2 equals to x1, x2 and x3. Then we have to solve this equation which is a minus lambda I x2 equals to 0, and lambda is 3 here. So we have to write this one in form of matrix. Then we get some system of equations which is this one. We have 0, 1, 4, 0, minus 1, 6 and 0, 0, 2. So first we have to solve this system of equations. With the help of this one, we get first one is actually x2 plus 4 x3 equals to 0, and minus x2 plus 6 x3 equals to 0, and 2 x3 equals to 0. So we get x3 equals to 0. If x3 is 0, then x2 will also be 0. And let x1 is any arbitrary number k. So the vector will be k 0, 0. Also we can solve with the help of cross multiplication method. So this is the method. After solving by cross multiplication, we can also get the vector of same form, which is 1, 0, 0, where k is any arbitrary number. Now we have to find the third eigenvector corresponding to eigenvalue lambda equals to 5. Then again we have the same system. We have a minus lambda I x3 equal to 0, lambda is 5 here. Then we get the this system of equations in which we have minus 2, 1 and 4, then minus 3 and 6. So we can solve these equations, or we can assume any of the x1, x2, x3 as arbitrary number. So we can solve directly. If we are solving directly, then we have minus 2x1 plus x2 plus 4x3 equals to 0, minus 3x2 plus 6x3 equal to 0. And let we have x3 as k. Let x3 as k. Then what will be the value of x2? We have minus 3x2 minus 6x3, or we have minus 6k. So x2 will be 2k here. After putting these values in first one, we get minus 2x1, then plus x2. x2 means we have 2k. Then we have last one, which is 4x3, means 4k equals to 0. We have minus 2x1 plus 6k equals to 0, or we have minus 6k. So we have x1 equals to 3k. So we get the vector which is 3k, 2k and k, or we have 3, 2, 1, which is the required eigenvector, or we can solve with the help of cross multiplication method. So we get the required eigenvector. So these were the few examples related to eigenvalues and eigenvectors. Thank you. That's all for today's class.